Problem 1. Deterioration of buildings, bridges, and other structures as a result of rusting of iron costs millions of dollars every day. Although the actual process requires water, a simplified equation is shown below, and rust is the product. They want to know delta H of reaction in kilojoules when 0.25 kilograms of iron rusts. Okay, step 1, we're going to want to convert. We're going to want to know how many moles are reacting, because this number they tell us on the right is essentially per like stoichiometric mole. So we're going to want to find how many moles of this iron is reacting. So if we have 0.25 kilograms, we can, let's get this into grams first because we're going to use the molecular weight. In 1 kilogram there are 1,000 grams, and the molecular weight of iron is, let's see, where is it? Oh, right there. Okay, 55.85 grams per mole. Okay, and then so we know there are 55.85 grams in 1 mole of iron. And if we do this, the kilograms cancel, grams cancel, and then we're left with moles of iron. So we got, oh, my battery's low, 0.25 times 1,000 divided by 55.85. We get 4.48 moles of iron reacting. Okay. And now we can do stoich. So we know we have 4.48 moles of iron reacting. And for every 4 moles of iron that react, we will get 1 of these quantities of energy released. So you can just use the stoich ratios if that makes sense. And let me just show you what I mean. So we know 4 moles, for every 4 moles of iron that react, we will get this much energy being released. I'm gonna get rid of the negative because I'll just figure out what the sign is at the end. I think that'll be more it'll be more clear. Okay. So multiply the top, divide by the bottom. 4.48 times 1.65 times 10 to the third divided by 4. 1,846.5 kilojoules. Okay. Okay, so we are down to B or D, it looks like. Is it positive or is it negative? And let's see. This is a exothermic reaction, so therefore it's just going to stay negative. It's not going to change. Yeah, we don't need to overthink that one. This one's just negative, so it's going to stay B. 1B? Yeah. Problem 2. Using the following data, calculate delta H in kilojoules for the following reaction. So we get some final reaction here at the bottom, and they are going to want us to somehow combine these 3 reactions to get number 4. Okay, and when I look, let's start with the products that do show up in reaction 4, because we know those ones aren't going to be canceled out. So I see first that there are 2 N2s on the reactant side, and the only equation that has N2 in it is 1. So I know I'm going to need 2 of reaction 1 in that same direction. So if I add 2 of reaction 1, I'm going to have 2 N2s. I'm going to have 6 O2s, 2 H2s, and then that is going to make 4 HNO3. And since I times it by 2, I'm going to need to multiply my delta H by 2. So negative 414.8 times 2 is 829.6. Negative, that is. Okay. All right. So we have the like N2s down basically. Let's see. Let's look at this one. That N2O5 only shows up in the second reaction, and it's on this one it's on the reactant side, so we're going to have to flip it. We're going to have to flip the direction as well as multiply it by 2. So from the second reaction, if we flip it and multiply it by 2, we are going to get 4HNO3, which is then being turned into 2N2O5, and then 2H2O. And once again, I can multiply my delta H by -2 because I flipped it and I multiplied it by 2. So 218.4 times -2, you get -436.8. Okay, now O2s also don't cancel, and I have 6 O2s right here. Well, from the first reaction, we're contributing 6 O2s on the reactant side. So in order to get to 5, we're going to want to have 1 O2 on the product side, which is going to have to come from equation 3. And we can get that by just adding 1 equation 3, because O2 already is it already has a coefficient of 1. So if I just add 1 of reaction 3, I get 2H2O, which is turning into 2H2 and 1 O2. And I didn't change anything, so I'm going to keep delta H the same. Okay, so let's see what cancels now. I got that the O2 is going to become a 5. So here, let me do this. If I were to add this up, I know my O2s are going to become a 5 because there's 1 on the product side, 6 on the reactant side. These are going to completely cancel. Same with water. Same with hydrogen. And then I'm going to get my 2 N2s will be left. I'll have the 5 O2s. And then those will be turning into 2 N2O5. So this is just a sandy check there. This matches that. So looks good. So if that all looks good, let's just do these now. I'm just going to add these values up. -829.6 minus 436.8 plus 483.6. Delta H equals -782.8. There we go. Okay, -782.8. D. 2D. 3. For which one of the following reactions is delta H reaction equal to the standard enthalpy heat of formation for gaseous pneumonia? So here we're just looking for a reaction. We know that the heat of formations for a species are based on 1 mole, the reaction where it's 1 mole of the product. So we're just looking for the reaction that has pneumonia in a stoichiometric ratio of 1 as the product, which this reaction is the only one that does. So 3B. You're just looking for the reaction that has the product you're looking for the delta H formation as the product in a 1 stoic ratio. 4. Pentaborane burns vigorously in oxygen to give that species and liquid water. Calculate the delta H reaction for the reaction in kilojoules per mole. So we know that the delta H of the reaction equals the delta H of formation of the products, I'm going to call that prod, minus delta H formation of the reactants. So, and what we can do to calculate these is we can take the stoic ratios and times it by the delta H formation of the species and then add them together. So for example, the delta H formation of product is going to be 5 times the delta H formation of, this species, plus 9 times the delta H formation of this species. And then you could do the same thing for delta H reactants. I'm just going to write out the whole the whole thing. So our delta H of reaction is going to become 5 times negative 1,273.5 plus 9 times negative 285.8 plus this is minus actually, minus our reactants, which are 2 times 73.2, and we also have oxygen as a reactant, but it's elemental, so we're not going to include it. It would be essentially the same as including 12 times 0. So I guess we can include it, but the heat of formation of the elemental species is just 0. So it's going to look like that. So if we throw this in our calculator, 5 times negative 1,273.5 plus 9 times negative 285.8. This gives me negative 8,939.7. And then that's minus 2 times 73.2. I get 146.4. And this equals 9,086.1. And I omitted units, but we are in kilojoules per mole because we did not change the units from our delta H formation. So here's our final answer, 9,086, and that's negative. I forgot the negative. Negative. So that leaves us with C, 4C. 5. Methane combusts with oxygen and air to form carbon dioxide and liquid water. Calculate delta H reaction for this reaction based on the delta H reaction data for reactions 1 and 2. So let's first write out what this reaction is. So they say methane is combusting, which means it has O2. Actually, let me write the phase too. It's also gas. And we are forming, combustion forms CO2 gas. And they tell us that water is liquid. Okay. And to balance this, 2, 2. Okay. So now we're going to have to use the reactions they give us, reaction 1 and 2, to somehow get to this sort of reaction 3, the total reaction. And actually, reaction 1 is the same. It's just water is in a different phase. It's in gas instead of liquid. So, in order to get to reaction 3, we're going to want to flip reaction 2 and add it to reaction 1. So let me rewrite reaction 1. Gas plus 2O2, gas. Okay, now, so I know the delta H reaction for this. It's negative 802. I didn't change anything there. Kilojoules per mole, or just kilojoules. And then reaction 2, we're going to want to flip. So I'm going to want to cancel this water, this gaseous water on the product side. So I'm going to want a gaseous water on the reactant side. So I'm going to need to move it to the left. So I'm going to flip it. So reaction 2, I'm going to flip it. I'm going to put 2H2O of gas on the left, which is forming 2H2O of liquid on the right. And now I also have to flip my delta H reaction, which is going to become negative 88. And now if we were to add these together, those two would cancel, and you would get the overall reaction, and you would also get this overall delta H reaction that we're looking for. So if we do this, if we just add negative 808 to negative 88, you get what is that, negative 890? Negative 890 kilojoules. D, oh, that's a terrible circle. 5D. 6. The combustion of methanol is this reaction. Compute the heat of combustion for 1 mole of methanol using the enthalpies of formation listed below. Okay, right off the bat, if you use the method that I showed in the previous problem, you could potentially get this answer, which is exactly double what the correct answer, I believe, is going to be. And that's because methanol is a stoichiometric ratio of 2. So when you get your final answer, when you get the answer, it's actually per 2 moles of the methanol, so you're going to want to divide it by 2. I just want to point that out real quick in case that's potentially why you got it wrong. But I'll show it now. So we know that delta H of reaction is equal to the delta H formation of the products minus delta H formation of the reactants. And we know, if we just start writing this out, I'll do this. Delta H reaction then is going to look like, let's start with carbon dioxide. So we have a stoichiometric ratio of 2, so 2 times negative 393.5 plus the other product, which is water, 4 times negative 241.8 minus the reactants, which methanol, which has a stoichiometric ratio of 2 times negative 238.6, and then oxygen has a heat of formation of 0 because it's elemental, so 3 times 0, or you can just ignore it. So this is going to come out to be 2 times negative 393.5 plus 4 times negative 241.8. So the products are going to turn into negative 1754.2. The reactants are going to be 2 times negative 238.6. Those become plus, so negative 1754.2 plus 477, you get delta H of reaction, so delta equals negative 1277. Now this would be if we were assuming a stoichiometric ratio of 1. So if there was some like arbitrary like product or other species, this is for like 1 mole of like reaction continuing. But we want to do it for 1 mole of methanol, so we're going to need to divide by 2 because it is a stoichiometric ratio of 2, and we want it per mole of methanol, not per 2 moles of methanol. So I hope that makes sense. If we take the number we just calculated and divide it by 2, you get negative 638.5. Okay. So that gives us A. Seven, calculate the wavelength in nanometers of light that has a frequency of that. So we know, let's see, we're looking for wavelength and they give us frequency. We know wavelength and frequency are related through this relationship where V is the frequency, lambda is the wavelength, and C is the speed of light, which is a constant, which is approximately this. And they tell us the frequency, which is already in seconds, so that's fine. Okay, I was going to convert it, but we don't have to because it's in seconds. So if we just plug this in, 4.62 times 10 to the 14th reciprocal seconds equals the speed of light over wavelength, which is what we're going to solve for. Divide over your frequency, multiply over wavelength. If I rearrange this, that would look like this. That would look like that. Okay, so if we throw this in our calculator, you get a wavelength of 6,493.5 meters, which is 6,493.5 times 10 to the 9th nanometers. There are 10 to the 9th nanometers in 1 meter. That's a useful conversion. So, which answers this? Let's see here. Wait. Looks like we got a unit wrong somewhere. Okay, the right answer is C. So my number is right, but I got a unit majorly wrong. Did I put in my calculator wrong? Oh, I put in my calculator wrong. Oops. Oopsie doopsie. Okay, hold on. Okay, hold the phone. These aren't right. Let me just redo it real quick. Okay, what you actually should get is this. And then when you convert that, yeah, you're going to get the 6.49 times 10 to the second nanometers. Okay, and then that's answer choice C. There we go. Problem 8. Which one of the following arrangements of electromagnetic radiation begins with the lowest energy left and increases with highest energy right? Okay, so if I know from memory, my electromagnetic spectrum looks something like this. You got UV, I'll call this the visible, and then it goes to red. And then it's infrared, and I also know that microwave is on this side, and X-ray is right here, I believe. Okay. So, and then there's more outside of that, but I know these are the 4 or 5 easiest ones to remember. And I also know that IR is in the direction of the lower frequencies, so frequency is going to increase this way. And I know that frequency, how do you spell frequency? I know frequency is correlated to the energy. So as frequency increases, so does energy. Therefore, microwave is the lowest, and then IR, and then visible, and then UV, which looks like E. 8E. Nice. So this one, you kind of just got to know your spectrum, or at least enough of them to do process of elimination, and then also that frequency increases as you go towards UV, and frequency is correlated to energy, which I think that's kind of intuitive. 9. The number of distinct emission spectral lines that originate from electron transmissions between the first 4 energy levels in a hydrogen atom is. So we know that between an energy level jump, so say I have an excited electron in the 4th energy level, and say it jumps down to this 3rd, or I have another situation where my 4th jumps down to the 2nd. These are going to lower energy, but we know energy is conserved, so where's that excess energy going? It's going to be released in a form of a photon. And these 2 photons will have very distinct, different energies, so they will each show up as a distinct spectral line. So like this one will be a spectral line, this one will be a spectral line. So how many of these unique drops do we have? Well, let's just count them up. So I have the 2 I just drew, and then if we also start in the 4th energy level, we could also just go straight down to the 1st. That's all we could have from starting from the 4th. If we start from the 3rd, we could also go down to the 2nd or the 1st. And if we start in the 2nd, we could go down to the 1st. If we count these up, 1, 2, 3, 4, 5, 6, there's going to be 6 distinct spectral lines. Calculate the energy in kilojoules per mole of 1 mole of green photons. Okay, so energy of photons, we know that E equals hv, and h is just Planck's constant, but we don't know v, which is the frequency that gives wavelength, so we know this is equivalent to E equals hc over lambda, and h is Planck's constant, which is 6.626 times 10 to the negative 34 joules times seconds. C is the speed of light, which I'm going to round up to 3.0 times 10 to the 8th meters per second. And I know lambda, that's just 525 nanometers, but why did I draw a dash? That's nanometers. But my speed of light, my C, is in meters per second, and my lambda is in nanometers. So we're going to want to convert this into meters to make the units check out. So we can just do this. That's the conversion to meters. Let's plug everything in. E equals 6.626 times 10 to the negative 34 joules times second. C, let's do this. Oh gosh. C, which is this number all over lambda, which is this number. Lambda is the wavelength. All right, so let's see here. Seconds would cancel, meters would cancel. This is going to be the energy in joules. Let's throw this in our calculators. Planck's constant. Planck's constant times speed of light divided by our wavelength in meters. I get 3.79 times 10 to the negative 19 joules. And this is the energy of one photon. So if I move this, this is essentially the joules per one photon, and they want the energy of an entire mole of them. So if we want to go from photons, which are a particle, into moles, I know that there are an Avogadro's number of particles or photons in 1 mole. So if I set it up like this, my photons cancel, and then I'll get joules per mole, and one more, they just want kilojoules. So 1,000 joules, this should be multiplied. There's 1,000 joules in 1 kilojoule. Okay, now my units are going to be kilojoules per mole. So we take that number from before, times it by Avogadro's number, divided by 1,000. I get 228.01, which is E, 10E. Okay. 11. A hydrogen atom in the n equals 6 energy level emits a photon of wavelength that many nanometers. What is its final energy level, n, of the atom after it emits the photon? So they want, they're essentially mapping the energy change associated with the jump between energy levels. We calculate this with the Rydberg equation, which is 1 over the wavelength equals the Rydberg constant times 1 over the higher energy level squared minus 1 over the lower energy level squared. Yes, okay. And also, when I was saying earlier that we're mapping this to the energy, 1 over the wavelength is corresponded to the energy. So that's what I was just mentioning earlier. Okay, so we are going to be solving here for N1. So if we just start plugging stuff in, first let's convert 410.2 nanometers equals 410.2 times 10 to the negative 9th meters. So 1 over that. The Rydberg constant is, I'm just going to write it in. I'm not going to write it twice. The Rydberg constant is 1.097 times 10 to the 7th, and that's inverse meters. And then 1 over n1 squared, which is what we're solving for, minus 1 over 36. Okay. Let's start throwing stuff in our calculator. 1 over 410.2 times 10 to the negative 9th gives me, I'm going to do 2 steps here. So I solved this, and now this is sitting in my calculator, and I'm going to divide this over. I'm going to do these 2 steps at the same time to save some space. Okay, so if I do that, let's see, divide over the Rydberg constant, I get that 0.222 equals 1 over n1 squared minus 1 over 36. Okay, and let's add over, so let's take the 0.222 and add on 1 divided by 36. I get that, so if I do that, I get 1 over n1 squared equals 0.25, and then I know that n1 has to equal 4, or, 2, because 1 over 2 squared would be 1 over 4, and that equals 0.25. So n1 equals 2. 11b. The total number of s atomic orbitals and p atomic orbitals, respectively, for the principal quantum number n equals 2 are. So if I just start writing out the full configuration, you have 1s2, 2s2, 2p6, 3s2, 3p6, 3d10. And they want to know about the second energy level. So we can just look at this. And I have 1 s orbital and I have 3 p orbitals. The reason I know that is because this number tells me the number of electrons in the orbitals, and I know I can hold 2 per orbital. So if this is showing 2 electrons, that's 1 orbital. If this is showing 6, that's 3. Also, I just know that's always how many are in each energy level. There's always 1 s orbital, 3 p, if there's any. So we got, let's see, what is that, D? 12D. 13, the radio station of Lafayette broadcast pop music at that frequency, and they want to know the wavelength. So we know that frequency and wavelength are related through the equation frequency equals the speed of light over wavelength. And pretty simple equation. They just give us the frequency and we can just plug it in. But we're going to want to do some conversions here. So our frequency is 96.5 megahertz. And 1 hertz is equal to a reciprocal second. And mega, the prefix, is times 10 to the 6th. So this is the same as 96.5 times 10 to the 6th reciprocal seconds. And then our speed of light is 3.00 times 10 to the 8th meters per second. We're going to want everything in the same units. So if we just take the speed of light and divide out the frequency, so if I solve this, I can just write it like this as well. So then my wavelength is going to be, if I just plug these in, my seconds would cancel and I would just get meters. Okay, let's do the speed of light divided by my frequency. I get 3.11 meters, 13B. 14. What is the energy of light in kilojoules per mole with wavelength of that many nanometers? I know that the energy of one singular photon is equal to Planck's constant times frequency, which is the same as Planck's constant times the speed of light over the wavelength. And they give us the wavelength in nanometers. So let's, my lambda equals that. They give us this in nanometers. Let's convert this into meters through that conversion. And I've wrote them enough times, so I'm not going to write like a key anymore, but E is going to be equal to Planck's constant, which is 6.626 times 10 to the negative 34 joules times seconds. Speed of light is 3.00 times 10 to the 8th meters per second. Divide that by the wavelength. Okay. Meters cancel, seconds cancel. We are left with the energy in joules of one photon. So let's throw this in our calculator here. Planck's constant times speed of light divided by the wavelength in meters. I get the energy of one singular photon is 3.56 times 10 to the negative 19. Now, this is in joules, and it's essentially of one photon. So if I want this in kilojoules per mole, I'm going to have to do two things. I'm going to want to go from photons into moles. So I know that in 1 mole, I want that on the denominator. So in 1 mole, I know there is an Avogadro's number worth of particles, in our case photons. And I also know that there are 1,000 joules in 1 kilojoule. So when we do this, the number of photons cancel, joules cancel, you get kilojoules per mole. So take the number, the energy from last time, times it by Avogadro's, divided by 1,000. I get that the energy in kilojoules per mole is 214.5. Okay, 214.5 looks like that one, right? 14C, nice. 15, light emitted from an excited state hydrogen atom with an electrons transitioning from level 5 to 4 will have blank energy and blank wavelength than light emitted from emission between levels 6 and 5. So, if we don't know this one off the top of our head, we know the relationship here is the Rydberg equation, which is 1 over lambda, equals the Rydberg constant times 1 over the higher energy level squared minus 1 over the lower energy level squared. And I don't even know. Let's just compare what wavelengths we would get. Let's just compare. So say I have no idea what this is, which I actually don't. Let's just compare these two outcomes. Okay. So this is 1 over 25 squared, or 1 over 25 minus 1 over 16. This is, oh, wait, I put them in the wrong sides. Oops. Oopsies. This should always be a positive number. Oh. This, inside these parentheses, should always be a positive number. So that's how I knew I put these on the wrong side. I get these mixed up a lot. You want the lower energy level on the left. I feel like I say that wrong a lot. Okay, anyways. This is going to give me 0.0225 R, R times that number, if that makes sense, what I just did there. And then the other one is 1 over 25 minus 1 over 36, which is a smaller number. But since it's inverse, this relationship is inverse, this situation has a higher number of this value, which means it has a lower wavelength. And lower wavelength means higher frequency, which means higher energy. Okay, hope that makes sense, the correlations I just drew there. So 5 to 4 will have higher energy, and the wavelength will be lower. 15, what is that? 15A, wonderful. What frequency of light will bring the electron in ground state hydrogen level to level 3? Okay, so once again, we're looking at the Rydberg equation. Let me write that. Maybe, does yellow look good? We'll try yellow. 1 over lambda, the wavelength, equals R, the Rydberg constant, times 1 over the lower energy level, minus 1 over the higher energy level. And now we are going to want the frequency instead of wavelength, and we know they are related through the fact that frequency equals the speed of light over lambda, and lambda equals speed of light over the frequency. So if I sub that in, I will get that the frequency over the speed of light equals this. So now I have an equation for frequency. And I want to bring the electron from ground state, which is 1, it's the first energy level, to level 3. So, let's see here. What frequency? I'm gonna multiply over the speed of light, and I'm gonna start plugging everything in. So the frequency equals the Rydberg, which is 1.0097 times. No, there's only 1 0. Oops. 1.097 times 10 to the 7th, and that is reciprocal meters, times that by the speed of light, 3.00 times 10 to the 8th meters per second, and then times that by 1 over 1 squared, which is just 1 minus 1 over 9. So 1 minus 1 over 9 is, I'm going to do that one first. Okay, actually, I'm going to plug all this in my calculator. So I did 1 minus 1 over 9, times that by the speed of light, and then times that by the Rydberg constant. And I get that the frequency is equal to 2.925 times 10 to the 15th. And let's see what my units are. So that reciprocal meter is canceled with that, and then this is just reciprocal meters, which a reciprocal second, and a reciprocal second is a hertz. So let's see, what's our answer here? Okay, is that right? 16D? Yeah, 16D. The only reason I'm a little upset is because I would think that would get rounded up to 2.93, but whatever. 17. What are the proper NL values and the number of orbitals for sublevel 2p? Well, I know N is the principal quantum number, and more or less it is the energy level. And when I write them in this form, the leading number is the energy level. So this is just 2. So my first number is 2, so it's not those two. That's a lot of 2s. Okay, L is the type of orbital, and our type of orbital is that we are a p, and p is equal to 1, because I know it kind of goes in descending order. So we know S is the first one that's filled up, and then P, and then D, and then F, and they start at 0, and then you just count down. So I know, as long as I know S starts at 0, and that you count down like this, P's filled up next, so it's kind of makes sense to call it the 1. So not A. So I know it's 2. I know it's 2 comma 1. And what's the third one? Number of orbitals. There's 3 orbitals. There's always 3 orbitals. For each one of these, you increase the number of orbitals by 2 every time. So this one has 1. S has 1. P has 3. D has 5. F has 7, not 6. This is also apparent kind of when you see number of electrons in a so I know it's B, but this is apparent when you see number of electrons in each orbital. So a lot of times you'll see like 2s2 and then like 2p6. The fact that the s orbital has 2 electrons implies that it is one orbital, because each one orbital holds 2 electrons. And sometimes maybe you've even seen like these arrangements, like where this might be S and this might be the P, and you might have an electron going that way and that way. Each one of these orbitals can hold 2. Anyways, I'm rambling. 2, 1, 3, answer choice B. Good. Which one of the following orbitals is represented by the radial probability distribution plot pictured below? I don't even care about the probability plot. Look at that. Energy level 3, L0, so I know it's S. So I know it's 3S. I know it's C. I don't know why they give you the plot if they're just going to say that. But regardless, I know that this is a S plot, and I know it's in the 3rd energy level because it has 2 nodes. These little node density areas are called nodes, where electrons can't or don't seem to exist. And that as you go up for the S energy level, or for the S orbitals only, as you go up each energy level, you add on 1 node, starting at 0. So 1s has 0 nodes, 2s has 1 node, and then 3s has 2 nodes, etc., etc. And these nodes are just areas of no electron density, or no probability. It's where electrons don't exist. So when I see 2 nodes, that tips me off to the 3rd energy level, in case they didn't give you this. If they give you this, I don't see why you need the graph to solve this. But anyways, 18C. 19. How many valence and core electrons are there in a neutral silicon atom? So let's find silicon. Let's find the periodic table. It's up here somewhere. Here we go. Okay. Silicon is right below carbon. So I know, let me write the electron configuration. Okay. I know the electron I know the electron configuration for silicon is going to be 1s2, 2s2, 2p6, 3s2, and then 3p2. Valence electrons are the electrons that are in the highest energy level or exist after the highest energy level. So it's going to be these 4. So for valence, we are going to have 4 electrons, and then the core is just everything else. So these, the core is going to be, 10? So 4 and 10. 20. Which one of the following is the correct shorthand condensed ground state electron configuration for a neutral titanium atom? Okay, I'm going to stop scrolling to the periodic table, and I think you should just open it up on another page or something. But when you look at titanium, let me write the full, oh my goodness. the full configuration. So once you find it, it's in the fourth row, fourth column, and when we write this, it's going to be 1s2. Why does it keep making those lines? 2s2, 2p6, 3s2, 3p6, 4s2, 3d2. Because it's the second element in that 3D column, or the 3D row. And if we want to shorthand this, we're going to find the noble gas that comes before it, which is going to be argon. And argon has a electron configuration. Oh my god. Argon is an electron configuration of this. Yeah, this is argon. So if I wanted to shorthand titanium into this, I could write it as this argon, and then essentially plus, this is what argon's taken care of. So I'm going to add on the remaining. So it just becomes that. So argon, and then 4s2, 3d2. 20d. Which one of the following lists the correct order of increasing radius from smallest radius left to largest radius right? So I'm going to write the number of protons each one of these has. Aluminum has 13, magnesium has 12, sodium is, oh my goodness. Sodium is 11, fluorine has 9, oxygen has 8. And they all have the exact same electron configuration of 1s2, 2s2, 2p6. They all have that exact same, you can fact check that if you want. They all have the exact same electron configuration. So what's going to determine how big our atom is? It's going to be determined by how strong the nucleus can pull in the electrons. So a stronger nucleus will pull things in tighter and have a smaller radius. The more protons you have, the stronger you can pull. So aluminum is going to have the lowest, magnesium is going to have the second lowest, etc., etc. So we're just going to arrange these in orders of highest atomic number to lowest, which is what A gives us. All right, I got a periodic table for these next problems. 22, which one of the following elements has the largest first ionization energy? So we got boron, nitrogen, phosphorus, silicon, and carbon. Let's find those. So boron, we got boron, nitrogen, phosphorus, silicon, and carbon. So we're up here. And I know that the elements that go in this direction will have high ionization energies. If you remember that, then it's nitrogen. Reason being, nitrogen is going to have more protons. When you compare nitrogen, let's compare nitrogen. If we compare nitrogen to like carbon and boron, they all have the same. Their outermost electrons are all in the 2p shell. So these are what you would be pulling from to get that first ionization energy. So you're pulling an electron from the same shell, but nitrogen has the most protons, which means it's going to hold on to these the strongest. So that therefore nitrogen will outdo these two. And then when we compare nitrogen to silicon or phosphorus, let's just look at phosphorus. Phosphorus's outermost electrons are actually in the 3p. So if we think about our model of the atom, or our simplified model of it at least, for nitrogen, you're pulling electrons out of like this 2p orbital, which is a lot closer, and it's going to be a lot harder to take those out than phosphorus's, which are out here. It's going to be a lot easier to pull one out from the 3p orbital than the 2p. So nitrogen also beats out phosphorus, and for the exact same reason, it beats out silicon. So nitrogen is our winner here. First ionization energy, it means how hard is it to pull away the first electron. 23. The successive ionization energies for a certain element are 578 for the first electron, and then we have a huge jump to the second electron to 1820, a smaller jump to the third electron at 2750, and then another massive jump to electron number 4 and 5. Okay. So these two seem to be grouped together, and so do these two. So I'm going to predict those two are in their own orbitals respectively. And if I know that these two are in their own orbital and they're surrounded by two other orbitals, they have to be in the s orbital. Because because if there's only two, I know there's only these two electrons in said orbital. The only orbital that has two electrons in it is the s. So this is an s2. And if whatever this is easier to remove, that means it's like to the right. So I'm going to say this is, let me keep it blue. I'm going to say this is a P1. It's probably a P1 or a D1. Right? And then these ones are harder to remove, so I know they're going that way. So it's going to be something like a P6. Right? So I'm just writing out generally, like I'm leaving what the energy levels are blank, because we can fill those in. There'll probably be multiple right answers here. We can use the same periodic table as before. So which ones fit this criteria? We're looking for something that has one electron in the p orbital or d orbital, which would be these. These are the d orbital ones, and then these are the p orbital ones. Do any of the answers match those? Yes. 23D aluminum. And if we were to fill this in, this makes sense because this is what's this? This would be 2, this would be 3, and then 3. So that's the back 3 part of the electron configuration of aluminum. So that checks out. You got to just look which energy levels are the same. So this is the big part right here. You got to recognize that those two are the same, and those two correspond to 2 electrons in the same orbital, which has to be s. That's really the big takeaway. And the one, this is like 1 electron in a p or d orbital. 24. Which one of the following equations represents the second ionization energy for aluminum? The first ionization energy would be the energy required to lose 1 electron, which would be this, and to do it again, it would just be this. Simple enough. Energy required to remove the second electron. So that leaves oops, I did not mean to put a 2 there. That was a mistake. That leaves us with answer choice C. 25. Which one of the following elements is most metallic? So, here is my periodic table. Something like this. And I know metallic character just trends this way. And it makes sense if you think about it. These are These are the metals over here in this region, and then these are the metals. So it makes sense that it would trend that way. Also, if you think about it, a lot of by definition, organic stuff is like carbon based, and carbon is right there, so it's going to have a very low non-metallic character. Everything up here is going to form covalent bonds. So if the bottom left is where the metals are, let's find out where our answer choices are in the periodic table, and then just see which one is the most bottom left. Phosphorus is right here. AS is right there. SB, this is convenient. SB is right below it. TE is to the right and iodide to the left. Which one is the most bottom left? Whatever SB is. Okay. Between which of the following pairs of elements is the difference in metallic character the greatest? Okay, let's do exactly what we did for the bottom problem, or the above problem. If you didn't watch the explanation, I'll redo it. Okay. Crappy periodic table is fine. Metallic character trends that way because, down here is our metals, up here is our non-metals. And yeah, I think that's kind of intuitive. Anyways, let's look at where our answer choices are and see which ones are the farthest distance away. Oxygen is right here, and RB is... that is a massive gap. Okay, oxygen and iodide, those are pretty close. It's definitely not B. RB and iodide. Okay, those are pretty far away, but oxygen is, I guess, less metallic in a sense than iodide. So I'm going to say A is still a better choice. Lithium and oxygen. Rubidium, I think that's what RB is. Rubidium is more metallic than lithium, so I'm going to say it's not D. And then lithium and rubidium, those are both metals, so there's not as big of a gap. 26A. Okay, 27. The electron configuration of a zinc 2+ ion is, so let's find zinc. Zinc's right here. This is in the 3D row, so the last orbital it's filling up is 3D. And let's see, it's atom number 10. So it's going to have 10 electrons in that 3D orbital. So let me first, this is an ion, it's got a 2+ charge. Let me first write the ground state configuration for this, for a neutral zinc. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then 3d10. Now, when we lose the 2 electrons, which 2 electrons are we going to lose? It might be intuitive to think we're going to pull from the 3D because that's what we filled up last, but we're actually going to pull from the 4s orbital, because even though we're filling up the 3D last and it is higher initial, the 3D orbital is higher energy initially. When it's all filled up, the 4s actually is higher energy. So those 4s electrons are going to come off first. So all you need to know is that when you have these transition metal elements and you form ions, they're going to pull off those s electrons that are in that higher energy level first. So this is our electron configuration for zinc 2+, and that's answer choice E. It looks like 27E. Yeah. 28. Which one of the following is a isoelectronic series? This just means same electron configuration. Iso, the prefix means same, and then electronic. So which answer choice do all these elements have the same electron configuration? Well, when I first look, answer choice C is sticking out to me because they all have the same charge, that being there's no charge. They're all neutral, but they're all different elements. So they can't possibly have the same electron configuration. So if I were to write the ground state electron configuration for a neutral sulfur and a neutral chlorine, they wouldn't be the same because chlorine has one more electron. It would have a different one than sulfur does. So it can't possibly be C. And it's the same deal for D. They all have -1 charges. But fluorine has a completely different number of electrons. It's a fluorine minus outermost electrons are going to be in the 2p6, whereas the chlorines are going to be in the 3p6. So those are not the same. So these aren't the same, neither of those two. Can't be B either. And for the exact same reason, it can't be D. So we got A and E as our choices. And just from memory, E looks like a great choice because we have neutral neon, and I notice we also have sodium 1+. So if you take the electron configuration of a sodium and take away an electron, it'll give you the electron configuration of neon. If you add 1 to fluorine, it'll get you the electron configuration of neon. And then if you add 2 to oxygen, it'll get you there. So E looks like the right choice. You can fact check this if you want. Every single one of these atoms has a 1s2, 2s2, 2p6 configuration. And answer choice A, if we just take a look at this one real quick. Let me get rid of this mess. Answer choice A, we got a boron 5-, which looks like it has the same configuration as neon. And then SR 4-, where is SR? SR is all the way over here, which no way, even if you add 4 electrons to it, there's no way those two have the same electron configuration. So it has to be 28E. 29. Electron affinity values for phosphorus, sulfur, and chlorine are listed below. Which one of the following statements best explains the trend in electron affinity values? So we know that electron affinity trends in this direction, the same as electron negativity, and conceptually it's kind of similar to electronegativity, where it's the ability of electron to pull or hold on to more electrons. And chlorine has the greatest magnitude. Let's find these on the periodic table. They are right here. And if I write the number of protons they have, 17, 16, 15. The reason chlorine has this greater ability to pull onto electrons is because it has more protons and it has a more effective nuclear charge. And that looks like answer choice A. They're saying it increases across a period, which this is true. The periodic table, it looks like this, you know. And as we go across the period, the number of protons is increasing. So A is true. And that's the reason why the electron affinity is higher. B says the exact opposite. It's not B. C, the principal quantum number n of the outer electrons increases across the period. This is not true. So in this group right here, we are in the all of these elements, their outermost electrons are in the 3p for all 6 of these. So that's not true. And if I just write, you know, the configuration, phosphorus is going to be 1s2, 2s2, 2p6, 3s2, 3p4. Is phosphorus 4? No, phosphorus is 3. And then if I were to write the other two, it would be the same deal, but sulfur would be the outermost one, would be 3p4, and then chlorine, this would be sulfur, and then, you know, chlorine would be 3p5. Anyways, I'm just trying to show that their outermost electrons are all in that 3p. So C and D are definitely not true. Okay, 30. Which one of the following sublevels is filled last? Okay, well, let's write our little diagram and just brute force check this. I'm going to do, so the only way, I'm not writing this from memory. I'm going to go down in the energy level, or the principal quantum number. I'm going to go down this way, and then across, I'm going to add on a orbital every time. So I'm going to start 1s, 2s, and then 2p, and then 3s, 3p, 3d, 4s. I'm going to need to fit 5 in here. 4s, 4p, 4d, 4f, 5s, 5p. I'm not going to write the other two because they're not going to fit. But you could write, you know, 5d, 5f. Okay, why is this useful? Well, I know they will fill in a very distinct pattern on this little thing I have here. They will fill diagonally in this direction. That looks bad. Red looks bad. Let's do blue. They fill diagonally. So 1s is going to be filled first. And if we do another diagonal line, just descending, 2s is filled next, and then 2p, and then 3s, and then 3p, and then 4s. So we can cross off 4s. That's the first one filled up. And we can just keep going down, and then 3d, which is a choice, and then 4p, which is also a choice, 5s, which is also a choice, and then we get down to 4d, which is going to be the last one to fill up. So when you write out this diagram, you know that they always just fill up diagonally, and you can just draw. If you can write out this, which I think it's pretty easy to remember, just write down the descend energy levels and then add an orbital every time you go down. You know they fill up in this diagonal pattern. So therefore I know 30 is D. 31. Which one of the following elements has a ground state electron configuration of this? The outermost orbital is 2p, and we are 3 electrons, or 3 elements deep in that 2p. Boron is 1 electron in, so boron's outermost one would be 2p1. Carbon is 2 electrons in, so carbon's outermost would be 2p2. Nitrogen is 3 in, so nitrogen would be 2p3, which I believe is what they had. Yeah, so this corresponds to nitrogen. 32. Which is the correct order in decreasing atomic size for the following elements? And they give us some choices. So let's find these on the table. Cesium down there, that's pretty massive. Sodium lithium, boron, fluorine. Is that everything? Looks like it. Okay, they want decreasing atomic size. If you just remember purely from memory, atomic size goes this way, so smaller stuff points up there. Fluorine is the small one. Reason being, let's say why, because I think if you know why it goes that way, it makes it a lot easier to remember. So let's first look at the columns. As you go down a column, you add a energy level. Oh God. As you go down the column, you add a energy level every single time. So when we compare lithium to sodium, say this is my lithium atom and this is my sodium atom. Lithium has only 2 energy levels worth. Actually, there's some blue. Lithium has only 2 energy levels worth of electrons, whereas sodium has an entire third one. You know, lithium's electrons aren't, its outermost electrons aren't as far away. Sodium is a whole nother energy level. So as you go down, you add one of these rings, nearly a ring, every single time. So cesium's definitely the biggest of these 3. Sodium's a little bit smaller, lithium's a little bit smaller than that. Now, how about going across rows? Well, as we go across the row, you add protons, and you do not add energy levels. So whereas you're not adding rings, if we compare a lithium atom to a fluorine atom, I'm going to erase this. Let's compare this now to a fluorine atom. We still have 2 energy levels. You know, nearly the electrons by default are nearly the same distance away, but fluorine has 9 protons compared to lithium's 3. So in a sense, fluorine can pull on those electrons 3 times harder. I don't know if that's actually what it is, but it's got a lot more. It can pull a lot harder on those electrons. So it can suck them in farther. That's why as we go across rows, they can pull in harder and pull stuff in closer. So let's look at our answer choices. Fluorine is the smallest, so it's not any of these bottom 3. And then it should be fluorine, boron, and then lithium. And then you go down the row. So it looks like A. 32A. Which one of the following elements has the largest first ionization energy? Let me clean this up. Although it probably is going to be a very similar explanation. Okay. 33. Let's find these again. Sodium, chlorine, calcium, Te. I don't know what Te is. Te and then bromine. Okay. And they want the largest first ionization energy. Ionization energy is the energy to remove outermost electron. And if you just want to know the trend, it trends this way. So increasing ionization energy goes this way. Fluorine has essentially one of the highest first ionization energies. Why is this? It's because as you go down groups, as I previously mentioned, you add energy levels and elements become a lot bigger. So let's compare sodium to calcium. Or should we do that? Let's compare chlorine to bromine. Okay, we're going to do chlorine and bromine. So here's our nucleus. Okay. Bromine has, let me do this. Let me move. Okay. Bromine is a whole other group down. It's a lot farther away. So when we're comparing the ionization energies of these 2 elements, we are essentially comparing the energy to remove this electron versus this electron. We're looking at the energy to remove an electron in the 2nd energy level versus the 3rd. And you don't need to know this equation, but just for relationships, the attraction forces between the nucleus and the electrons, it looks like this. So this is Coulomb's law. And I just want you to notice here that as you go farther away, which is r squared is the distance, as you go farther away, you are going to have significantly less force on those electrons. So this electron out here, this bromine outer electron, is way far away, and it's getting pulled on way less. So it's way easier to remove. I think that's kind of intuitive. You know, the electron that's farther away can be pulled out easier. Okay, so as we go down rows, you lose ionization energy. Now, how come as we go across groups, ionization energy increases? Well, if we compare a sodium to a chlorine, let's compare a sodium to a chlorine now. So, yeah. Okay. Where is sodium? Okay. The chlorine actually does have a third. I forgot to draw the third one. Whatever. You got what I was saying in the last point. Okay. This sodium atom, its outermost electrons are in the 3s1. And this one singular electron is really easy to remove. So it looks something like this. Say it just has one electron floating on this in this spot up here. If we were to compare sodium to neon, per se, sodium and neon have nearly the exact same strength of the nucleus, 10 to 11 protons. It's exactly the same. But sodium's outermost electron is just sitting in an entire higher energy level. It's sitting way farther away, and it's a lot easier to remove. And also, if you think of ionic bonding, which you've probably seen by this point, the elements in this part of the periodic table always form positive parts of the bonds. So, for example, if we have salt, sodium chloride, the sodium always has the positive charge, the chlorine always has the minus charge. This is because sodium gives up that outermost electron really easily. It's really weakly attached, as opposed to chlorine, which chlorine has 7 electrons in that outermost shell, and it's got like one perfect gap where it can accept an electron really easily. So the electrons going up, or the atoms going up in that direction, have really high ionization energies. So of these choices, I erased all the choices, but chlorine's definitely the highest. 33b. The 34. The first 4 ionization energies of a certain element are listed below. This element is most likely in which column of the periodic table? Okay. When we're looking at the ionization energies, you got to recognize when ionization energies are similar to each other, because that implies that they're probably in the same orbital. So when I'm looking at these two are, roughly in like the 1,000 range, and then these two look way different. They're like 15,000 range. There's massive jump. Although 900 is not exactly the same as 1800-ish, they are similar when you compare this massive jump. So this is telling me that my outermost 2 electrons are in the same orbital. And the only orbital that has 2 electrons is the s. So essentially my outermost shell has 2 electrons in it. And the only orbital that houses 2 electrons is the s. So if I had 1 electron there, it would be something in this row. But since I have 2, it's something in this row, which is the second column. 34D. To elaborate a little bit more, because perhaps that wasn't sufficient, you got to recognize that these two have very similar energies to remove, which means they're in the same orbital. And I also know that the only orbital that could house 2 electrons is the s. So if this went on, say they gave me data for, E1 through E6, say they all had like 1,000, and then like 1,100, and then 1,200, blah, 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 blah. If it looked something like this might imply I might have, my outermost electrons might be in the p. I might have 6 p electrons. And then if there was a giant jump down to like 30,000, then I'd know I'd be then tapping into the next s, or whatever orbital. So you got to look at which of these are similar energy, because that's telling me those electrons are in the same orbital. And because I have 2 of them, I know the only orbital that has 2 electrons in it is the s. And elements with 2 electrons in the outermost s orbital are the only ones, are only, column 2 elements. So yes, there we go. 35. The first, second, and third ionization energies of boron are those numbers, respectively. How much energy would it take to remove the valence electrons from 1.5 moles of boron? So they want to know how much energy, they want to know how much energy it takes to remove all 3 valence electrons. So I can do this. This is summative. So I can just add these up. I can add up the energies it would take to remove 1 mole of all 3 of the electrons. What does that give me? This gets me 6.89 millijoules per mole. And if I can take 6.89 millijoules per mole and times it by 1.5. Oh, is this megajoules? Oops, I meant to say megajoules, whatever. Times it by 1.5 moles. My moles cancel. And I get 10.335 megajoules, which is answer choice E, 35E. 36. For which one of the following properties does magnesium have a larger value than barium? Okay, let's find these. Let's go to yellow. Oh, it's small. Oops. Nothing wrong with that. Okay, magnesium, barium. Let's see here. Okay. Atomic radius. This is definitely not true. Magnesium has 12 protons, and it only is occupying 3 energy levels, as opposed to barium's much bigger nucleus, which has 56 protons, and it has 6. So this is supposed to be the nucleus. It has 6 whole energy levels, much bigger. And I think that's pretty intuitive. As you go down, you add more protons and stuff, the element gets bigger. I think that's pretty obvious. B, ionic radius, exact same reason as answer choice A. It's bigger. So that's not the case. Higher first ionization energy. This is true. So maybe I should go back actually to my hyperbolic. Okay, that's barium. It is a lot harder to remove an electron that's this close than it is something this far away. So barium's outermost electron, which would correspond to the first ionization energy, is much farther away. And it's way easier to remove something that's that far away, because of Coulomb's law. You don't even know this equation. Maybe I kind of regret writing it, but this is the force that's exerted on that outermost electron. And because barium's is so much farther away, it's way less force pulling on it, it's way easier to remove. So magnesium has a much higher energy to remove this electron. So therefore it has a higher first ionization energy. Let's look at D and E as well. Magnesium does not have more protons than barium. It says it in the atomic number, so that's definitely not true. E, atomic weight, basically the exact same thing. You can just read that number. So 36C. Which one of the following has the largest radius? Okay. Let's first, I'm going to write the electron configurations for these. 1s2, 2s2, 2p5, 1s2, 2s2. It gains an electron, so it goes to 2p6. This one loses an electron, so it goes to 2p4. And this has the same as answer choice B. Okay. Answer choice B and D have the same electron configuration. So whereas before, often we compare how far away the electrons are to get us radius, but answer choice B and D have the exact same, electron configuration. The electrons are the same distance away. So the only governing factor that will impact the radius between answer choice B and D is which one is a stronger nucleus to pull in the electrons. Neon is one more element to the right of fluorine. It has 10 protons to fluorine's 9, so it can pull on those electrons a little bit harder and bring them in. So if this is fluorine, this is neon. It's got a stronger nucleus, so it can pull those in a little bit more. So D definitely does not have the largest radius. I'm going to erase my horrible drawings too. Okay, so now we're just looking at fluorine. Now, in the opposite case, A, B, and C all have the same amount of protons, obviously, because they're all the same element. It's got 9, right? Should double check that. Yeah, it's got 9. Okay, these all have the same nuclear strength. So the only thing that matters is the electrons and their configuration. So what you need to know here is that, so this is essentially our situation here. We're in the second energy level. One case has 4 electrons. Now, if you were to go from answer choice C into the case for A, if you add in a 5th electron, this 5th electron is actually going to repulse the other ones. It's going to repulse these, and they're going to move just a tiny bit farther away. As you add electrons, you get bigger. So, out of these 3 choices, C is the smallest, B is the biggest. Also, I think it's intuitive in the sense, if you were to imagine adding one more, if we went to Fe, or fluorine 2-, you'd have to add a whole nother energy level, which obviously is going to be way bigger. So I think it's kind of intuitive in that sense to see a more hyperbolic example of adding electrons makes you bigger. Yeah, 37B. Great. 38. Which one of the following has the ground state electron configuration for... Oh, has that ground state electron configuration. Okay, let's just write these. Okay, magnesium is it's in the 3s. It's in the 3s row. It's the second element there. So if it loses, let me write this. 2p6. The ground state magnesium would have 3s2, but since it's got a 2+ charge, it's losing 2 electrons. It loses those. Neon has this. Sodium is, I'm assuming, right next to magnesium, because I know where this question is going. Yep. So ground state sodium looks like this. Ground state sodium looks like this, but it's got a +1 charge, which means it loses 1 electron. So that goes away, and then oxygen, it's gaining 2 electrons. If oxygen gains 2 electrons, it will have the same configuration as neon, which I already wrote. Those are all the same, all of the above. 38E. Question 39. A chemist made a Beer's law plot with standard of aqueous cobalt chloride at a particular wavelength as shown here. If she tests a sample of cobalt chloride and measures an absorbance of that number at the same wavelength, what is the concentration of the sample? Okay, so even if you don't know Beer's law, they give us the plot, and they want to know the concentration at this absorbance, and they give us the relationship. So the absorbance is about there, and on the x-axis we have concentration. So we can just plot it, and it looks like it's somewhere between 0.004 and 0.006, so that gets rid of those choices. And luckily they also just give us the relationship, so we can just plug it into this equation. What they gave us is the y-axis variable, so I'm going to put that as the y, and then I'm going to solve for x. So if they give you the relationship like this in the equation, you don't even particularly need to know Beer's law. So if I minus over the 0.0997 and then divide by 150.05, you get that x is equal to this number, which makes A correct. 40. In visible spec, the wavelength of maximum absorbance is usually used for spectrophotometric analysis because, okay, now we can explain this. So now when we're using Beer's law, well, let's do a quick, if I have a solution, say I have a beaker, and I want to shoot some light at it, I shoot some light through it, less will come out the other end because part of it's absorbed. I think that's pretty intuitive. And this is a useful phenomenon for us because we know that the amount absorbed is going to be proportional to three things: the molar absorptivity, which I'll explain in a second, the length, which is just how long this is. Obviously, as you can imagine, if there's more solution in the way, it'll absorb more. And then the concentration. As you can imagine, if instead of, I had, X species in there, if I had more, so I'm showing dark blue now, if there was like more species in there, it might absorb even more because there's more species in there to absorb. So that's why we have path length and concentration. Those are really just telling us how much species is in there that's absorbing. The molar absorptivity, on the other hand, is a property of the material and the species. And so let me draw this real quick. If I put absorbance on the Y, and then I can put wavelength on the X. Per one material, a material will have different absorptivities for the same of these properties, but with different wavelengths. So I feel like I'm explaining this bad, but you can have something like this. So for a particular species, this species might absorb more at this wavelength. So then if we're going to want to use this highest wavelength in our examples, in our sample, in our experiments, because that will give us the greatest change in absorbance, which will give us the greatest quantities. So if I were instead to use a wavelength of this, say this is, the visible region is from about 400 to 700-ish. So say I use something in this region, the changes in absorbance would be smaller and I would have less to notice. So if I wanted to measure, usually you use Beer's law to measure the concentration of a sample. So if I had two samples, and I want to know the concentrations of these, right? So I have one, it's lighter, there's less concentration. I have one that's got a little bit greater concentration. I want to know the numbers of these. I'm going to want the maximum change of response of my absorbance to measure the difference in concentration of these. So in order to get that, I'm going to want the wavelength that's going to give me the maximum change in absorbance. So therefore, I'm going to want this maximum wavelength up here, which is the maximum absorbance that I can get. So let's see, if we look at the answer choices, A, the change in absorbance per unit change in concentration is the largest at this wavelength. Yeah, that's true. And I think, and just to finish my last point, so if we were to shoot two beams at this, if I pick something that has really low, if I were to pick something in this region, the absorbance that comes out, the absorbance that I measure might be exactly the same, versus if I pick one that will have a massive change, it'll be a more observable change. It'll be a more observable difference. Anyways, B, the change in absorbance per unit change in concentration is smallest at this wavelength. That is definitely not true. It's the exact opposite. C, chemical substances only absorb visible light at a single wavelength. No. So if we look at this, spectra, you will get absorbance at this point. You'll get absorbances at all these points. So generally, for the entire visible spectrum, you'll get some absorbance. If you didn't, what C is saying is if we had a plot that looked like this, if this was 0 absorbance and then 1, like that. But that's not what it looks like. It's a curve. So C is also not true. D, chemical substances absorb visible light equally well. That's not true as well. D is proposing that this graph looks like that. It's a straight line, but it's not. And you can look these up too. Just Google, absorbance spectrum per wavelength. So that leaves us with answer choice A. 41. A spinach solution was prepared to determine the concentration of iron in spinach. A 10 milliliter sample of the original spinach solution was diluted to a volume of 30 milliliters with DI water. The absorbance of the diluted spinach solution was that number. Use the plot below to get the concentration of iron in the original solution. So similar to the problem we saw at 39, I think. we can just essentially plot this and use the graph they give us. They say that the absorbance is that number. On the plot that looks like that. I don't even know why I bother plotting it. Let's just use the equation. 0.285 equals this. So it equals that. If we solve this, I'm just plugging y in. They tell me y, so I'm just plugging it in. Okay, I get x equals this number. Now this is so the iron is what's absorbing stuff, and they want the concentration of iron in the original solution, which is just a 10 milliliter solution. But we diluted it. So the concentration in this diluted solution is going to be, it's going to be 1/3 of it in the original solution because we diluted it by a factor of 3. So the concentration in the original solution is going to be 3 times that in the solution that we just measured. So if we just take this number and times it by 3, we'll get our answer. So if I just do that, take that last number, multiply it by 3, 8.866 times 10 to the negative 5, which is C.